Hey guys, today we will be doing problem 509 called Fibonacci number. And the problem states that the Fibonacci numbers, commonly denoted as f of n from a sequence called the Fibonacci sequence, such that each number is the sum of the two preceding ones, starting from 0 and 1. So f of 0 is 0 and f of 1 is 1. And it's the function is defined recursively, so f of n is equal to f of n minus 1 plus f of n minus 2 for all numbers for all n greater than 1. So given a number n, we want to calculate f of n. So for example, if the input was 2, that's equal to f of 1 plus f of 0, and that's equal to 1 plus 0. So the answer is 1, and so on and so forth. So if you haven't tried this problem, please consider pausing the video to try it out. But otherwise, let's jump right into it. So since, let me copy all this. I'm gonna go over here, and I'll do this in the color pad. So since this function is defined recursively, it makes absolute sense to write the function recursively. So let me start with writing a function called fib, and takes in number n. And it says right here f of 0 is 1, or f of 0 is 0 and f of 1 is 1. So if n is equal to 0 or n is equal to 1, then we want to return n. Great, that was simple. Otherwise, we want to return fib of n minus 1 plus fib of n minus 2. Great, so this seems pretty simple enough. Let's make sure this is working properly. So let me do fib of 2, 3, and 4, and I should expect 1, 2, and 3. So let's see. Let me just write up the Fibonacci sequence. So the Fibonacci sequence is 0, 1, and then 1 again, then 2, then 3, and 5. So if I call fib of 0, I'll get this first element, and then if I call 1, 2, 3, 4, I'll get that corresponding. So let me do a loop for I in range 0, 1, 2, 3, 4, 5. Is that? I want to do 7 now. I want to print the fib of I. And let's see what we get. Ooh, that's not good. It's because I forgot to add a return statement here. Great. So we do get what we expect: 0, 1, 1, 2, 3, 5, and also 8, because that will be the next Fibonacci number. Great, because 8 is equal to 5 plus 3. Cool. But one thing that you'll notice is that if we try to call fib of 20, or go up to 20, let's see what happens. Currently it runs in 1.3 seconds to calculate 7 Fibonacci numbers, but if we change this to 20, it still completes it really quickly. But let's do fib of 50. As you can see, it's taking a long time to compute the larger Fibonacci numbers. And the reason for this is that while we are calculating the Fibonacci numbers, we're doing a lot of duplicated work. Because if we look at fib of 5, that is equal to fib of 4 plus fib of 3, right? And now we have to do fib of 4 plus fib of 3, and that is equal to, if we I guess expanded this, that was equal to fib of 3 plus fib of 2. So this is the fib of 4 section, and the fib of 3 section looks like this. Fib of 3 is equal to fib of 2 plus fib of 1. And as you can see right here, we're doing duplicated work because we're calling fib of 2 twice here, whereas once we already know what fib of 3 is, it's we can just not compute it twice. Again, we're calling fib of 3 twice here, up here and down here. So the solution to this is the solution to this specific scenario that I have is called memoization. What we can do is we can keep a dictionary to keep track of all the numbers we already computed. So we could just create like a global object if we want to. This. But okay, yeah, we can just do this if we want to. So at the beginning of the function, if the object is, I guess, okay, let me do it at the end of the function. So at the end, this is the result right here. So we have the result, and we want to store this result in our memo dictionary. So we'll say that the result of calling fib of n is equal to this result that we just computed, and we just will return these results. Great, but when we first call the fib function, if we have already computed the fib of n, then we should use the cache results. So if n is in the memo, and I just want to return the memo of n. Great. So if I rerun this function, as you can see, it completes much faster because we're not doing any of that duplicated work. Cool. So this is nice. And if you're curious, you can see that I guess if we wanted to print out memo, it would have 50 elements, or I guess, yeah, it'll have like around 50 elements, one for each input, except for 0 and 1. And so that's 48 inputs, or 48 elements. So there is a way of actually making this better. And to do that, we could re-engineer how the function actually computes Fibonacci so that it's not recursive. So what we could do is we can use we can first use an array to, I guess, keep track of this Fibonacci sequence, and we will fill it in. So like we'll start it with 0 and 1, and then we can append the next Fibonacci number to this number, to this I guess list, and so on and so forth until we reach the length n. But this doesn't really solve our problem because this will have the size equal to n as well. And what I'm trying to do is I want to make this faster than I want to make the space consumption of this function to be smaller than n. So what we could do instead is, if we look at the computation really precisely, the computation depends on the last previous numbers only. Therefore, once we computed fib of 1, the next number, fib of 3, we only require fib of 2 plus fib of 1. Therefore, we don't really need this number anymore. And the next number, which is 3, we only need to add these two numbers together. So we really don't need any of these numbers anymore. So what we could do is, at any point in time, we only need to store 2 variables to compute the next Fibonacci number. So therefore, we can just have 2 variables called a and b, and we'll set a to be the first Fibonacci number and b to the second Fibonacci number. And what a represents is, b represents the last number that we computed. A represents the second to last element that we computed. So we won't need this memo object. We could use it if we want to, as we're calling Fibonacci multiple times. So let's actually keep it. And we'll keep this statement where if n is in memo, then we want to return n. I see. Yeah, never mind. Let me just remove it. So, okay. So, let's see. This is still true. And since we're not using A and B yet, we can move this to here. And now we have a number n, and we want to loop over, we want to, let's see, if n is 2, then we want to generate one more Fibonacci number. We already have 2 Fibonacci numbers, but if n is 2, we want to generate one more. So looks like we want to do a loop for n minus 1 times. So for n, for index in range of n minus 1, we want to generate the next Fibonacci number, which would be equal to a plus b. And now since we generate the next Fibonacci number, we want to reset what a and b are. So a will be equal to b, and b is equal to c. Because if a was 1 and b was 2, the next Fibonacci number would be 3. And at the end of this loop, b gets promoted to c, and a gets promoted to what b was. Alright, hopefully that makes sense. So now, at the very end of this, b will contain the number, the last Fibonacci number that we computed. Alright, so we just return b. Now let's see if this works. I'll change this back to 6 so we can see. And yeah, it looks like it's working properly. So let me copy this and try to submit it. So I'm going to return fib of n. And I'll run this first. Great, looks like it's working for this example. So I'll just submit it. Great. So this is one of the better solutions, but there is still one solution that is even better. Currently this will take constant space because we only have like 3 variables that we keep track of, I guess 4, but it's a constant number of variables, and we don't use recursion, so we don't I guess we don't have to pay that cost. And also, yeah, that's basically it. And I guess it runs in a linear amount of time because we have to loop over n. But there's an even better solution where there's a closed form for the Fibonacci sequence, and if we use that, we can get a constant time, I guess return a constant time function. But you can take a look at that if you want. But for the purposes of this should be good enough. Great. If you like this video, please like the video, and that's it. Have a good day.